Hello, everyone, and welcome to another MLOps event, this time in New York, for sure, virtually. Here we have two our amazing speaker talking about larger scale recommenders. And before I introduce our speakers, I just want to mention that you can, if you have any question during the talk, you can ask your questions in the chat section. I will collect your questions and we'll discuss all of your questions at the end with our speakers. And without further ado, let's dive into the bio of our speakers. Mengdi Huang is a deep learning engineer at NVIDIA with 6 years of experience working in various deep learning-based AI research and application areas, including MLOps, recommender systems, and multimodal language, vision, and speech processing. Shashank Verma is a deep learning technical marketing engineer at NVIDIA. He's responsible for developing and presenting developer-focused content and various deep learning frameworks and libraries. He obtained his master's in electrical engineering from the University of Wisconsin-Madison, where he focused on computer vision, security aspect in data science, and high performance computing. So I'm sure you are excited too. I'm excited to listen to your talk. So back to you, Mengdi and Shashank.
Thank you so much, Peter, for the intro. So I'll start by sharing my screen. So that without further ado, let me start the talk today. So today the talk is about continuously improving the large-scale recommenders with MLOps tools and practices. And here's the agenda for today. So first, I'll give an overview. We'll introduce the use case for recommenders and why at NVIDIA we built NVIDIA Merlin, a framework to enable efficient building of large-scale recommenders. We discuss considerations around MLOps tooling and practices that will help enable a continuous improving of large-scale recommendation systems from development stage to production. Then we'll talk about Kubeflow for creating and managing our pipeline. And as we dive deeper into the second part of the talk with that use case, we'll talk about various components of the pipeline, their functions, and various considerations. Yeah, so this is the overview part. Since this is an MLOps summit, I assume most of the audience already knows what MLOps is. So I'll just briefly go through why it's complicated to build ML applications. So when we think about AI and ML, we mainly think about model development and model training. However, in reality, a lot of the complex tasks are required to build an end-to-end AI ML application. For example, we need to gather data, clean it, extract features, build feature stores, build models, provision resources for training, put the model in production for serving workloads, monitor performance, and so on. In this talk, we'll discuss recommender system as an ML application example and walk through the MLOps tools and practices for continuous improvement of large-scale recommender systems. So why did we pick recommender system as the use case? Recommender systems are a critical resource for enterprises that are relentlessly striving to improve customer engagement. They work by suggesting potentially relevant products and services among an overwhelmingly large and ever-increasing number of offerings. So let's look at a diagram on the right-hand side for a very simplified version of what a recommender system looks like. Give an input which contains an optional query and some information about the users and items. The recommender system generates a list of relevant items for the user. So for example, on an e-commerce website, the input would be users' previous purchases, item browsing history, a pool of items, etc. And output relevant items are a list of products. In real-world scenarios, the input changes all the time. For example, in the e-commerce case, when unexpected events, for example, the pandemic happens, user behavior changes drastically, which would include required gathering new data of new user behavior. For example, like people suddenly start getting masks or hand sanitizers overnight, and then updating the features and models and so on within a short period of time is required. So the ability to quickly and continuously integrate and deliver these improvements into production is critical for the recommender system to stay effective. This means that a dynamic recommender system needs to constantly evolve and adapt. This can be through digestion of new data or algorithmic improvement of the models. And such rounds of feature transformation and model training workflows may happen periodically or on an ad hoc basis, depending on use case. If the pipeline is suboptimal or slow, your costs can stack up. In essence, if your model has drifted from in production and is providing irrelevant recommendations, you better fix it as soon as possible. And if you have to do it often, it better be cheap. So yeah. So the takeaway from the last two slides are so first, ML model is only a small part of an MLOps system, the recommender system. And also the recommender system is a dynamic system needing to constantly evolve and adapt. So besides these two challenges, which requires good MLOps tools and practice to tackle, large-scale recommenders also presents unique challenges of its own. So in practice, it isn't too hard to imagine an e-commerce website with millions of users and items. And additionally, the datasets can be quite large, usually from hundreds of gigabytes to an order of terabytes. These poses a challenge's own kind of slow and complex ETL, slow data loading, and embedding tables too big for the hardware memory and throughput latency requirements. So the solutions we propose with NVIDIA Merlin and the MLOps tools tackles the above challenges. So what does the solution look like? So before I introduce the recommender system MLOps architecture in the next slide, let me briefly introduce the Merlin framework, which consists of ETL plus data loading component NVTabular, the training component HCTR, and the inference server component with Triton. So now we have the developer framework for building large-scale recommenders more efficiently. We need more tooling to operationalize the system, monitor and update it in production. So we can do it with MLOps tools and practices. The rest of this talk is about exactly the different components and considerations that may be required to do so. So let's look into the high-level MLOps workflow for recommender system using NVIDIA Merlin. This would involve a fully automated pipeline and continuous retraining. So let's look deeper into the architecture. So first, we start from the upper left corner. So it's data acquisition and validation. Starting from the beginning, we have fresh data coming into the data store. And then moving to the right, we have data preparation. Every recommender system starts with data about users, items, and their interactions. Data is collected and stored in a data store. And from the data store, a subset of data, for example, based on time range, when a number of features is extracted and prepared for the model training accelerated by HCTR. And then subsequently, once we have a model, we may want to run validation to ensure that it meets a certain standard for deployment. And then for the deployment and serving side, there are modules for deploying the model with NVIDIA Triton and monitoring its performance. An automated redeployment pipeline puts the new qualified model into production in a seamless manner. The number of GPU inference servers automatically scales up and down as needed. And then for logging and monitoring, monitoring modules continuously monitor the quality of the recommendation in real time through a range of KPIs, such as hit rate and conversion rate. So just let me just pause a little to kind of show that the red, the green boxes are kind of like the NVIDIA Merlin components. We see NVTabular, HCTR, and kind of the big Triton influence server here. So the logging components to talk about here is on the left-hand side of the big green box. So it was originally like not a part of Merlin, so it's definitely a good MLOps tools to be added. And monitoring modules can continuously monitor the quality of the recommendation system in real time through a range of KPIs such as hit rate and conversion rate. And then the modules trigger full retraining if the model drift happens, aka if certain KPIs fall below known established baselines. And then data validation module may ensure that the new data is as expected while also detecting data drift. So now that we have this in theory, let's see how it pans out in practice. To orchestrate this workflow, we'll use Kubeflow on GKE or Google Kubernetes Engine. So to give a brief introduction to Kubeflow, Kubeflow is an open source project to make deployments of ML workflows on Kubernetes simple, portable, and scalable. So it's cloud agnostic, which can essentially run anywhere Kubernetes can run. This can mean GCP like we do in our case study later, or it could mean AWS, Azure, or even on-prem. Kubeflow provides a variety of components for both the experimental phase as well as the production phase. So in our case, we are interested in the production phase on the lower right-hand side. And we want to leverage Kubeflow pipelines to orchestrate our MLOps workflow. So the Kubeflow pipeline is the one on the bottom here. The pipeline component is containerized user code meant to perform one step. This could mean a component for data transformation, training, and model validation, and so on. And to implement the ML workflow, many of these components could be chained together to form a graph. And next, my colleague Shashank will talk about a case study using Criteo, a large-scale recommender dataset implemented with NVIDIA Merlin components and orchestrated by Kubeflow on GKE. So hand over to Shashank.
Oh, thanks, Mengdi. Let me share my screen. So Mengdi talked about some of the overview regarding the case study that I'm going to present to you about. For instance, she talked about the high-level MLOps workflow and how Merlin components fit in it and enable like building large-scale recommenders. Right. So let's look at a case study with the Criteo data set on just 1 second. I think I need to go a little bit back. So the Criteo case study is an effort to take a large scale data set, which is the Criteo data set, and build a recommendation workflow with MLOps tools and practices. We do this because it's hard to understand what problems there are unless you try to build a solution end to end. And try it hands-on, right? So the Criteo dataset is one of the largest public domain datasets in the recommendation domain. It has over 1 terabyte of ad click logs, uncompressed click logs containing over 4 billion samples, right? That can be used to train recommender models and then predict the click-through rate. So, and just to give you a brief overview of the dataset itself, there are 13 numerical features in the dataset, which are integers, and 26 categorical features, which are hashed. And then there's also a label which corresponds to whether an ad was clicked or not. So this is exactly what we're trying to predict here. To go about building an end-to-end system, we break down the process into roughly 3 phases. These roughly correspond to different levels of MLOps, right? So beginning with level 0, in which we create the manual processes and the pipeline, which is just a bunch of loose scripts, configurations, definitions, and containers. These include data conversion, feature engineering, loading and training the model, as well as serving it. Right now, this is a very simplified version, right? Depending on your use case, you may have something like creating a feature store or building a retrieval model, right? Or business rule enforcement policy towards the end, just before you're going to display your recommendations. Note that this is, like I mentioned, a simplified version. The Criteo dataset only contains the interaction data, and that too is anonymized. There's no data on users, items, and attributes. So we don't, in this case study, we don't particularly look at candidate generation or final ranking in too much depth. We focus on accelerating the deep learning scoring part to predict whether the users will click on an ad or not. Next, on level 1, we create a Kubeflow pipeline on Google Kubernetes Engine. From the different components, we ensure that once the pipeline executes successfully, the model is hosted on an inference server like Triton. And then we add features like periodic retraining with, let's say, Kubeflow scheduler cron jobs or something. Moving forward, we add a little bit more complexity. In level 2, we will add more tooling and more important production considerations, like monitoring of model drift, monitoring based triggers, or adding a data validation and a model validation stage as well. So to begin with, in this slide directly borrows with the high-level slide that Mengdi showed earlier. This is a simplified architecture of a recommender built with NVIDIA Merlin components on a Kubeflow pipeline. And this roughly corresponds to the level 1 that I was talking about earlier. If you see some of the components, they kind of match the level 1. So starting from the beginning, we have a data store. In this case, the Criteo data set is stored over here. It is copied to a persistent volume first from the data copy component from the GCS store into a persistent volume. And this can be backed by a high-speed solid-state SSD persistent disk. And the reason that we do is because disk read speeds can have major implications on the data loading performance. Right, so you want to accelerate the whole pipeline, and we figured that we found out that like copying it to a persistent drive actually improves the performance while training. So the next component, this picks up data for transformation, which is the ETL and training component, storing features in a feature store if required, as well as a feature engineering workflow object. And this workflow object, right, will be used during inference to transform your incoming requests as well. So that's why we kind of store it for later use. If your use case has a candidate generation phase, you might want to build something like an index during this component. But in our case, we build the scoring model and using huge CTR. And then there's a model preparation component in which in level 1, this is just really a placeholder for components that will come in like for model validation later on, right? It just copies the newly trained model and adds some sort of versioning. It copies it to a model store, which can be picked up by NVIDIA Triton during deployment, right? And then finally we have model preparation, the deployment component, right? And the deployment component, what it will do is that it will launch the Triton inference server, and this component only really runs once. And the reason it runs once is that we want the inference server to keep running regardless of how many more runs of the pipeline there is. And then whenever there's a new model that is generated and stored into the model store, the inference server should automatically pick that up without any server downtime. And then there's a recommendation serving app. What it does is that it sort of sends the inference query to Triton and gets the responses, sends it back to the user. There's also a Kubeflow scheduler, and this pipeline runs periodically with fresh data in the GCS data store. So let's add some more complexity over here. This is fairly complex, but let's add some more. So we go to level 2 now, and you can see here there are paths for model monitoring and monitoring-based triggers. It also has a data validation component in the data preparation step. We also add inference tracking of inference metrics using Prometheus. And if you observe now, the loop is closed. We have a data collection module which logs the inference requests we use for subsequent rounds of retraining. In addition, there's also auto-scaling, which is not really shown here in the slide. This can be based on a user-defined custom metric to scale up and down the number of instances of the inference pod. In this case, the pod hosting Triton inference server, right? And this can be based on a custom metric. And in this case study, we chose the number of incoming requests or the load on the server as the metric to scale up and down. But you could define your own. For instance, a good one could be like something like GPU utilization or the GPU power usage is another one to determine like how loaded the server is, how much load the server is under. Sorry. So next, I'm going to talk a little bit more in depth about some of the different components that I mentioned in the previous slide. Let's look at data validation, and many of us are like data engineers and data scientists here. So we already know that the quality of data can make or break your model. Making sure that the data is clean and consistent can have the highest return on investment in machine learning lifecycle as compared to pretty much any other activity. And this is seen in practice, right? Unlike traditional code, ML models are unique software entities whose performance can fluctuate over time. And thus we must track the drift that is sort of, the drift in data that can happen after the model is deployed, right? But what does data drift mean, right? It is defined as the change in the distribution of data, essentially in the simplest terms. So how do we measure it? Naturally, we track the change in distribution of features over time using measures like JS divergence or any other reference statistics that you might want to consider when you're sort of developing your models during feature engineering, let's say. And this is exactly what the data validation module will do. Every time new data comes in, it will check its consistency as compared to a predefined baseline, and you could do any sort of action based on the result, like alerting the user or triggering certain components of the pipeline, or something like that. The high-level idea kind of remains the same among the different open source solutions that we have. Which is essentially to generate reference statistics from the training data or certain reference data during the development stage, right? And then you calculate statistics on that on the new incoming data or the fresh batch of data, and you apply those rules or reference statistics to find deviations or anomalies, and then you simply take actions based on the result. So moving on, let's talk about performance monitoring, right? Where you can use metrics like accuracy scores, area under the curve, precision, recall etc., to monitor the real-time performance of models once deployed. But then the question becomes that you need metrics like you need the ground truth itself or the labels for tracking these real-time predictions. So the ground truth can be obtained by tracking user engagement on the served recommendations. This is one way to do so. And in our demo, we have a monitoring module that runs as a separate pod in the cluster, and it essentially tracks the incoming requests and can trigger a rerun of the pipeline with new data to accommodate for changes in the data in the distribution. Right? How does it get access to data? So well, the recommendation serving app is keeping a track of the served recommendations, which is sort of the which is essentially the inference results that you have. It has information about the user query that went in, and then also the user responses. It is keeping a log of the essentially the user interactions or the user responses to the served recommendations. And then it sort of publishes it to a message broker, which is picked up by the performance module, monitoring module. So moving on, and what happens if the drift is detected? Essentially, in our case, we re-trigger the Kubeflow pipeline. And this could happen if the rolling AOC score, it goes below a certain predefined threshold. So let's talk about continuous training, right? Mengdi mentioned earlier that the recommendation model must evolve over time for its predictions to stay relevant. So the availability of new data or even new implementation of any component in the pipeline is an important trigger to re-execute the pipeline, right? There are different ways you can go about this. You can do periodic retraining, which happens on a schedule. It could happen on full data, or it could happen on incremental or just the fresh data using the previous checkpoint. This could be so. In our case, we use the Kubeflow scheduler to do so. And then there is triggered retraining, which is triggered by the monitoring module when it detects either the performance or the data drift the model performance or the data drift. It basically falls above or below a certain threshold. And there's also the ad hoc way of doing it, in which the user upon inspecting, or the developer upon inspecting the logs, they can trigger the pipeline from the Kubeflow UI or SDK. So there's a bunch of ways to go about this. And in production, if there's a surge in the number of inference requests coming in, your inference server should scale up automatically up and down to allocate and deploy new instances of the inference service to meet the surge in demand. Depending on your use case, you may want to trigger such scaling behavior based on your own custom metric, or even use a default metric like CPU, GPU utilization, or any other thing that you want, depending on your use case. The inference deployment can be, in this case, in this example, we used the average time spent by the inference request in the inference queue. If the load on the server increases, then the time spent by the incoming request in the queue goes up as well. And this can be a good indicator of when you might want to scale up, when you might want to scale up the service. To balance the increase in load, essentially the Kubernetes horizontal pod autoscaler, right? It can schedule another instance of the Triton inference pod on any of the freely available GPU nodes in your cluster. And then the HPA kicks in. If there are no nodes available in the cluster, then the HPA kicks in, and the GK node autoscaler can assign a new GPU node to the node pool. After a new node is available in the cluster, the pod autoscaler schedules a new instance of the Triton pod on the new GPU node, essentially, right? The load balancer can then route the pending incoming request to the new Triton pod. Subsequently, if the load decreases, the autoscaler can scale down the load, and you can save on compute. You can save on costs, so like that. We also have new technology in the latest GPUs called as multi-instance GPUs to improve utilization. It can partition, and for instance, it can partition an A100 GPU in up to as many as 7 instances, and each of them is fully isolated with their own high memory bandwidth, cache, and compute cores. So with this, you can scale with the granularity of having a part of GPU at once. So for instance, you can one part of the GPU could be out of 7, you could have like a partition with 3G 20 GB, which means that 3 out of 7 parts and 20 GB memory. So you could scale with that chunk, for instance. So that is one way to improve GPU utilization. And then you can sort of, when it scales down, you kind of save on costs that way. So I'm not sure how we are doing on time. It's 9:06, so I think we have 4 minutes. Let me jump straight to the conclusion. There's a demo here, but I'm sure you can find it.
To get started, we'll need to create a cluster with NVIDIA GPU.
Online. Let me go to the next slide. So what's next? So you can try out the demo. We have instructions for the whole thing, and for the whole thing available in a developer blog and in a user guide, as well as we have a developer blog for it. And then there's a GitHub repo, which contains all the code for the example. And then what would be, in conclusion, right? Recommenders need to constantly evolve to stay relevant. And then there's a requirement for retraining, in recommenders often, depending on the use case. This could be periodic or triggered by the monitoring module, right? The NVIDIA Merlin, it will accelerate the entire pipeline from ingesting the data to training and deploying your GPU accelerated recommender systems. And as you can imagine, there are many pieces missing from the demo or could be improved further. For instance, we could have live data drift monitoring visualized using a dashboard. That's a neat with a neat UI or something like that. And then in our case, we use Google Cloud PubSub for as the messaging infrastructure to sort of log the log the request to the monitoring module. And you could use this sort of adds a level of dependency to the GCP infrastructure. And you can use other messaging mechanisms like Apache Kafka or even RabbitMQ. What we observed in practice was that the data validation component, right, was extremely slow. It was not accelerated, meaning that, for instance, the Criteo, even 1 day of Criteo data can be as big as 40 gigabytes, right? And to generate statistics on that for validation can take a very long time, right? We couldn't get to sort of improve that part of the model, but it can totally be done, right? That part can be accelerated using custom NV tabular ops as well. And then we want to ideally think about how does the architecture change or scale when we have multiple such models being hosted at once, right? So there's a bigger model orchestration problem going on over there, which we haven't really covered so far. So I think that's all I have for you today. Thank you so much. So here are some of the resources like the demo, the blog, and there's a repo. So thank you so much.
Thank you. Thank you both, Mengdi and Shashank, for the great presentation. We have a couple of questions. And let's go into questions. So I think you answered this somehow, but maybe it's good to discuss it more. One of our participants asked that, what do you use for data store or feature store in model repo? For all of them, do you use the same tools?
So that's a good question, right? The data store, we use GCS, right? Because it gives us a lot of options for configurability. And in case you want high-speed storage options, it does provide you that as well. And another thing that I want to mention is that we really developed this sort of in collaboration with, some of the GCP folks, because they were trying to launch A100. They were going to launch the A100 GPU, and we wanted a workload, an example workload. Right, so there was some inclination to use sort of GCP infrastructure there, but in terms of the feature store, in our case, we don't really have a feature store because we are only focusing on the scoring part of the model. Right, as far as the model store is concerned, it is again a persistent disk that we're using. So they are they are essentially the same solution, which is a cloud storage.
Yeah, thank you. And our next question is, in the case of recommender systems, we know that the data are the patterns generated by the user item events. What statistics can be calculated with this framework when the feature is not a numerical attribute, but more co-occurrences of the events?
Can you please repeat the question?
Yes. The question is, what statistics can you calculate when the feature is not numerical attribute,
Right.
but more co-occurrences of events?
So I think even with non-numerical attributes, so for instance, the example that I gave, JS divergence, right? It's a sort of a distribution of features that we're tracking over time, right? For categorical sort of features, I'm guessing we didn't really focus that much in our demo on those, tracking those metrics. However, I'm guessing that you could have a distribution of let's say a histogram or something like that, right? Which essentially tracks how many occurrences of a certain category or the frequency of the bins, and then you can see how it's sort of varying over time. That will give you an idea of what should I say? It will give you an idea of if the incoming data over time is changing in the terms of if a lot of people are buying, let's say, a new object or a different object on an e-commerce store, right? So then the distribution of such feature could change like that. And additionally, what could happen is that there could be newer categories like the new object introduced, right, which are not previously part of the workflow. And in that case, you might want to find that early, right? And this can happen during the data validation stage when it can this can happen during the data validation stage as well. So yeah.
Thank you. And we have follow-up question regarding these questions that Gian Mario asked that histogram and the frequency of single items or users, he meant, but what about the co-occurrence of patterns, for example, in collaborative filtering? And how do we test if those patterns are drifting?
That's a good question. I'm not an expert on this specific matter, to be honest, so I might have to check back on that. So please feel free to contact me. I'll leave a link to sort of my email, and then so you can contact me on that, and I'll definitely get back to you on this.
Thank you. Thank you. That would be great. Let's go to the next question. How do you evaluate the accuracy of the models based on user engagement or activity?
How do I evaluate the models based on user engagement or activity?
Yeah, the accuracy of the model.
Right. So let's say your system, which is serving these recommendations, right? It sort of sends an inference query to the inference server to generate a set of responses, and then these ordered responses are presented to the user in a certain format. So what we are really tracking here is sort of how the user interacts with these, meaning that whether the user actually clicks on those recommendations or not. So based on that, based on tracking that, we figure out, what the ground truth in this case is, whether the user clicked or not. So that is how the occurrence of user response to the served recommendations is what we are tracking.
Thank you so much. So that was basically all the questions. And is there anything else that you want to add and mention at the end of the talk?
I may want to leave my email and contact for some of the questions that I fully did not know the answer to. So where can I do that? Can I do that in the chat?
Yeah, sure, absolutely. You can share your email at the chat section so our participant can reach out to you. So thank you, Mengdi and Shashank, for the great presentation, and thank you all attendees for being with us today. Thank you so much.
Thank you.
Thank you so much, Peter. I also just left my email in the chat.
Thank you.
Thank you.
So that would be great. So if anyone has further questions, they can reach out to you.